Hey, hello everyone. I'm Raffaele. I'm the Senior Technical Product Manager for MetaHuman. Now, that's the top half. Before we begin, this is a two-part talk. So after I'll be done with my half an hour, I do recommend you stay around because Matt's presentation is amazing. Now, it will be my privilege to take you through a tour of the MetaHuman framework. And let's get right into it. The mission statement for us is democratizing the creation of engine-ready, high-quality digital humans. Now, there's one bit that isn't obvious in that statement, which is that MetaHuman isn't a single piece of software or technology. Now, to communicate that, sometimes we refer to it as a framework. If you like the word better, you can also think of it as a content platform. Now, the point is that we do consider MetaHuman one product, but it is made of multiple collaborating parts, and many of them can be used independently or optionally. Now, the point of the talk is what is actually in this framework. But before we begin, it's worth going over the pedigree of MetaHuman. Now, at 2 years old, it might seem like a relatively recent product. It is worth noting that it is based on both bleeding-edge research as well as production experience from teams that have shipped a lot of content and technical demos. Now, everything that we ship or rely on is wholly owned by Epic and not reliant on external technology providers, and that makes it a fairly secure and consolidated technological basis. Now, since we occasionally get asked, this is actually a highly integrated team that is taking these things to the public. Our tools are continuously worked on by members of all of these groups. They all work in the same team space, they're in the same dailies, they work on the same code base. This is effectively an Epic product. Now, while MetaHuman itself isn't a single piece of technology, there is a very important key item at the heart of it. And that is that we have a large, varied, highly curated database of real data. Now, this, for us, is a continuing effort, and it spans from casting to fine-tuning the fit of each rig that goes into that database. Talent is cast so that we can increase the variety and coverage of face and head morphology that we have in it. Real people go through a very exhaustive scanning process that generates both 4D and photometric data. Now, that's a considerable amount of data that then goes through several steps, some assisted stages, some manual, some automatic, of a pipeline that generates meshes, rigs, materials, textures, a whole host of things. And finally, these highly curated items are the ones that are added to our database. Now, that is what gives us the ability to navigate and search what is effectively a continuous space of human features. Now, there's a couple of reasons why you will care about something like that. I mean, beside the fact that it's pretty cool. But the main thing is every increase that we have in the scope or the density of that database naturally makes all of our tools more powerful and the results far more varied and precise. Now, this being a tech talk, the idea is that you will be leaving with some useful information to understand when and how to leverage MetaHuman. I'd like to partition the problem space for the sake of this discussion, like in what we're actually trying to solve here, and start from disciplines and assets. Making digital humans hasn't just always been very hard work and a lot of hard work. It is also a wide variety of work. You need body meshes, head meshes, grooms, rigs, animation. Like, I imagine most of you know how much work it actually is. And assuming one has the resources and the time to produce these assets, they all need to be realized while being mindful of several qualities, and these need to be upheld. Fidelity, like if this needs to be a recognizable someone, this is especially true, what can you do to make sure it looks like that person? And there's a whole host of other things, right? Can the assets be edited comfortably? Do these assets fit your budgets, runtime, or storage, or what else? Are the assets manageable? Do you have all of the tools to establish various workflows? So there's quite a bit that needs solving. And once you've solved it, it is a long-term effort to actually maintain and let alone improve these solutions to stay on the bleeding edge of technology. So how do we go about it? Now, very quickly, we're going to go over what we have shipped or are about to ship inside the MetaHuman framework. Less than 2 years ago, we launched MetaHuman Creator. This is what put the name MetaHuman on the map. And when we say MetaHuman, most people probably think of this. It's incredibly accessible. It's very easy to use. It has a playful UX while remaining very powerful. And it is a web application, which makes it available to anybody with a browser, quite literally. Now, since launch, over 1 million users have created millions of MetaHumans, which goes some way to demonstrate that the scale and the strength of the backend is production ready. Now, just over a year after that, we released Mesh to MetaHuman. This pushed the engine integration. Before we had engine integration, it was the format of the assets that you would download, but this pushed it further. This is an engine plugin, and it gives users an entry point into MetaHuman directly from inside the editor. It requires that you run the editor because of that, obviously, but the workflow and the robustness mean that just about anybody can go from a scan or a sculpt to a great rig mesh in minutes. Not much later, we released DNA Calib, and this comes directly from Freelateral internal tools. It is part of what we actually use to produce rigs and such. It is for the more technically inclined users, and it gives access to the MetaHuman DNA file format, and that is the data format at the core of MetaHuman head meshes data. And for meshes, we mean static and scale both. Now, you can absolutely and thoroughly leverage MetaHuman without using it, but if you care about pipeline integration and deep likeness for some things that might be even a little bit more than plain humans, this can help a great deal. And if you've seen the keynote, and I gotta admit, I'm super excited about this one. This is what you would have seen. Now, MetaHuman Animator is a very powerful feature set. It will be available inside MetaHuman for Unreal. So same plugin that we released Mesh to MetaHuman for. We have already heard from some of our testers, this has literally changed how they work or even what kind of work they can take on. We'll go over some of the interesting use cases we've heard about. Now, we'll talk a little bit about what we make available that is out of engine, because there are pipeline needs and some people might want to work out of engine. But it is important to note that Unreal Engine is the one place where you do get everything. Now, everything we do is eventually transformed into interconnected UE assets. It's important that this is not an all or nothing deal. You can opt into assets based on what you feel brings value to your project and replace the rest or tailor it to your needs. Now, leveraging the engine asset park as is also means that managing these assets that we will create for you, that some of our tools might create for you, doesn't require any extra knowledge. Using MetaHuman doesn't bring any unnecessary dependencies into your project and build. So, we're finally getting to those partitions. What assets do we provide, and what can MetaHuman help you with? We'll start with the easy things. You can choose from different body types, grooms, and a collection of clothing. These are grouped together because all of these are discrete, handcrafted assets, and they are available from MetaHuman Creator. They're discrete choices, or at least they're discrete choices for now. And at export time, the correct variants that you've picked are exported as assets. Any necessary work, like groom binding, linking the colliders, all of that is done for you. And all of these come with fine-grained LOD choices. There are currently 18 body types in MetaHuman Creator, and like most, we separate heads and bodies. So we've also taken care of seaming, LOD syncing, and all of that. Now, MetaHuman bodies were made mannequin compatible some time ago. They weren't at the very, very first time of release, but they are now, which gives you access to a whole host of animation from our samples as well as from third parties. Now, quick tip, if you wish to use MetaHuman only for the heads, which is fairly common, you will have to take care of seaming yourself. We strongly recommend that you pick a body type. Don't ignore this choice. Pick a body type that is close to what you think you will need, because that will actually save you quite a bit of time when it comes to seaming. For clothing, there is a curated selection of handcrafted items. We have tops and trousers and shoes. These are contemporary designs, so if you're doing a period or a sci-fi piece, the look might not work for you. I will still suggest you don't completely sleep on these. At a minimum, they can be a very good starting point for you to get skinning and LODing templates transferred to your cuts. We also make sure that all of these fit all of our body types. And because MetaHuman has become pretty popular as an asset platform, you can find a lot more from third parties. If you get something from a third party, to remember to check what body types they support, because it might not be all 18. Now, MetaHumans also come with several grooms, and that goes from the subtle pitch fuzz on skin to full hairdos. If there is one you like, great. If not, they're actually very good sample content, to be perfectly honest. It's definitely worth getting at least a few, inspect them, look at how the groom binding works, look at how the LOD sync works, because that is functionality that if you bring your own grooms into it, you almost certainly will want to support. And it's also worth noting, like, not all, but most of these grooms also have been carded across all LODs, so they're pretty performance sensitive. Now, materials and textures have a little bit more nuance than just discrete choices. Our texture creation is also data-driven. The images and the assets come from something that we call texture synthesis, and some choices are currently discrete. That's a very small amount of choices that are discrete. But even those, like wrinkle maps and blemishes, actually come from our scan data, and when we generate the textures that you get, the maps that you get, they respond to the other parameters. So they do change based on other things that you set. But other parameters, like the iris or the skin color, actually originate from data and measurements, and they are in a continuum, and they are based on a statistical approach. So this isn't a plain color that is hooked there in the shader. Now, at export time, texture synthesis does all of the prepping, asset generation, does so at multiple resolutions. It's all the things that you would expect. It's very solid. All of the linking is done before the assets are packaged. And once they come into your project, which is what we were talking about before, they are straightforward to understand. They come in as normal textures attached to normal materials. So you can modify if and as you need it. There are maps for quite a few channels, and this is the bit where they are a little bit more than just simple groom binding assets. Linkage can be more involved. Some of the maps, like the wrinkles, are actually connected to animation channels so that you have the right triggering when your character expresses something. Now, head meshes, and with that we mean static and skeletal meshes here. This is where things start becoming pretty special. Like all of our parts, you do get battle-tested topology, you get consistent assets, fine-grained LODs for everything. But authoring is entirely in a continuous space, and things open up here quite a bit. UX, this is creator, and UX is very playful and intuitive. And we feel that this is where that notion of having a continuous, seamless space of human features actually starts shining through. And it enables like very unique manipulation tools. This isn't just linearly or bilinearly interpolating between a bunch of meshes. This is literally exploring our database. You can start from 1 to 3 presets and blend into that space quickly, and that will get you a good starting point. It gets you the first coarse approximation of what you might want. You can then move on to details, and these are more localized controls. Now, this bit has a very plastic, proportional modeling kind of feel, but again, in actuality, what you're doing here is exploring our database, and these manipulators like fundamentally move you into this n-dimensional space of human features. So if you've ever used it, most of the time it feels great. Some other times it feels like it's quite not getting there exactly where you want it. As we expand our database, that will start zeroing in more and more and more towards exactly where you place something. Okay, so by design, this process in MetaHuman Creator is meant to be in a bound space. Every possible result from it is well-behaved and plausible. Now, what's worth noting here is that skinning, joint shapes, displacement shapes, they don't come from discrete presets. If they did, you would have some overly safe and boring deformation. Each head in our database comes with highly polished rigs. So when you generate a MetaHuman, the rigs and the shapes that go with it are also generated appropriately from that continuous space. So you're guaranteed that every single MetaHuman coming from there is individually fully expressive as well as well-behaved. Sometimes, though, you need to push the boundaries a little bit or zero in on some specific likeness. And this is Mesh to MetaHuman, which was what we put in the first release of the Unreal Engine plugin. And it introduced a very powerful tool, Mesh to MetaHuman. Now, we designed this to be very, very easy to use, but it adds considerably to how far you can push a MetaHuman head. Now, as it stands right now, you can start from any mesh, choose a few views. Those are turned into frames, track the frames, feed our topology to that mesh, and then you can send that to our backend, which will do all of the rigging and everything. From there, you can choose to edit it further in Creator, or it will just appear in Quixel Bridge, and you can pick it up from there, which is why we're saying, in many ways, this is a new point of entry for MetaHuman, and it makes Creator, which remains like incredibly important, optional to your workflow if you decide that you don't want to access it. It's worth noting that when I say things like you need to track the frames or feed out topology, what I really mean is that you push a button and it usually just automatically works. Now, one way to think of this specific set of functionalities is it's as if it was a fine-grained search to look up your mesh in our semantic space and get the closest approximation possible of that volume that we can provide together with the full rig. Now, if Creator lets you explore within defined boundaries, Mesh to MetaHuman lets you push those boundaries by introducing a volume delta. Now, the image up there, it might be subtle, especially for someone watching these on video and not in person. But that subtlety makes a huge difference when you're trying to get really close to someone's specific appearance. So what happens here is that when you use Mesh to MetaHuman, first we take the mesh that was provided, then we look up a first approximation of that mesh in our semantic space. We record the difference between the volume of the mesh you provided and our find, and that is sent to the backend for rigging, and then the delta between the two is preserved, which is what you can see here. There are two things that come through from this image, I feel, and one is if you look at when the slider is fully to the left, you can see that our find in our database was incredibly close to the volume of the actress that you can see here. But you can also see that like just a few millimeters around the eyes can make a huge difference when you need very specific likeness. Now, if the input mesh is a cube, and believe me, a cube isn't the worst that we've seen people try, the system is robust. It will still do its best to approximate it, and it will then record a large difference. The rig is based on our find, right? So if the delta is very, very large, the mesh is likely to misbehave in some areas or with some extreme animations. But when you're looking for something that is very human or human-like, it can actually take quite a bit of punishment and get you great rigs in no time at all. Now, while we were working on this, we were also working on our performance capture feature set, which is what you now know as MetaHuman Animator. So all along, we were designing the workflow and everything so that it could work from footage as well as from meshes. If you use Mesh to MetaHuman, there is no need to learn absolutely anything new. Instead of importing a mesh, you can import footage. If you have a high-resolution stereo couple, it will be just the one frame, plus one for the teeth if you're really keen. Or if you're using a plain iPhone, you'll be using 3 frames. You track them, you fit them, and you get a rig. There's no manual intervention in any of the things that we have shown, like in our keynote or in the things that you can see at our booth. Now, these head meshes are in large part encoded as what we call MetaHuman DNA, and this is an asset that's about to come, as well as data and files. It is the core data format for MetaHumans, and it contains all of the parameters for meshes, rigs, and their attributes. Now, that data as a file comes bundled with any MetaHuman you download, and it has some pretty useful engine integration as is, like literally drag and drop it and you get a rig, which is pretty cool. But it's also, now that we released DNA Calib, something that you can open and modify. Now, DNA Calib is part of that toolkit that Freelateral used to deliver assets at the highest level for years. It is definitely on the technical end of the spectrum, but it is not so far that way that a TA or a TD that's comfortable with Python wouldn't be able to fully leverage it. It's a C++ library that gives some degree of access to the contents of the MetaHuman DNA file. But it comes with both the source code as well as the precompiled binaries, which makes it pretty easy to deploy. It has Python bindings, which makes it very, very accessible. and it has a very extensive reference implementation in Maya. So this is a library that you can use from anywhere. You can use it from a command line if you want, but if you want to see an integration in a DCC pipeline that is not directly inside UE, we provide that reference implementation for you. Now, beside the obvious benefit of inspection, right? You open a file, like you get a file, you open it, you see what's in it. The DNA viewer part of this, you can see the plugin as you receive it if you want to download it there, allows you to look at our DNA file, and it gives you some first glimpse about what we normally encode in there, which is you can choose what LODs you assemble, LODs you assemble, like what properties do you want in them. So this effectively allows you to build up inside Maya or elsewhere, like just the assets that you want to work on. Probably more importantly, though, is the MetaHuman DNA editing tools. Like, this is what allows you to take these things and synchronously, through our commands, edit things such as the global scale or the global position of the head, remove joints, rename joints if you have specific pipeline needs and you don't like how we name things. It's a perfectly valid reason to start using these, even if it's just to rename things. Now, once you're done with that, in your DCC app or from a command line, if you're adventurous, whatever works for you, you can export FBX files. You can export that DNA file that will get bundled with the FBX. And for all intents and purposes, inside UE, that will behave like if it was a MetaHuman. The only thing you're losing when you're using something like this is that you started deviating from what you get straight out of Creator, but you do still get all of the functionality. Okay, so last and possibly the most significant part of our assets are our rigs. Now, rig logic is effectively the rig. Now, it's the core of our facial animation. It is parameterized in semantic space. And that means things like brow up and down, jaw up, down, left and right, and so on. It is responsible to blend, interpolate, and trigger all of the joint animations from expressions, displacement maps, map parameters connected to your material, all of that. It is all done from this one place. It is a single central node. It is thread safe, and it can animate as many faces as you need it to. This has been shipped with a very large number of titles. So this is one of those things that comes from that long production heritage. Now, it's also worth noting about this that this is probably the only thing that we would recommend that you actually include in your build. If you're doing linear content, you don't have the problem. But if you're doing interactive experiences or games, this comes as an actual thing that you will want to include in your build, because it is very, very good for both performance and the footprint of how you manage animation. Now, we know that not everybody animates everything in engine just yet, which is why we also have a Maya version of this node, so that you can have full facial rig parity between Maya and Unreal Engine. Now, animating a flat list of hundreds of parameters might not be everybody's cup of tea. So we also have a faceboard style control rig, and that is far more animator friendly. Now, this rig too is available in Maya and Unreal Engine, and it's connected to rig logic the same way, guaranteeing that you have full data parity when animating faces outside of UE. There's also a lot of work that we constantly put into this, which is part of the backward solving. If you use control rig, you might know it for a fairly powerful feature, which is it has forwards and backward solve. It allows for a lot of neat tricks. When you look at the row curves on our rig logic node, and you look at how they map to the faceboard, that is a non-trivial mapping. So we constantly maintain and improve that backward solving for you. You can seamlessly bake things from the faceboard to the row curves on rig logic, or backward solve them the other way, losslessly. Like, you can do this many, many times, and your curves don't start deteriorating. Like, as you look at the character, it's still emoting and expressing exactly the same way. All right, so the whole point of a rig is that you want to put animation on it. At least normally that's how I think of it. We really should be closing with more details on what we revealed today in the keynote. MetaHuman Animator is a huge update to our Unreal Engine plugin. It is a true end-to-end system for performance capture, and it goes from your footage through the ingest, all of the steps, to final animation. It comes with everything. We provide camera calibration tools if you use stereo couples. iPhones are calibrated by factory. We take that into account. New assets that represent your devices inside the project, ingest through a convenient window, creating a full rig from just the footage, which is what I was talking about before, tracking and solving the actor's delivery from footage in the new performance asset, generating animation directly on rig logic or on the faceboard. And finally, taking that animation and applying it to the control rig faceboard, if you wish, through the backward solve. Now, that is literally everything that you need for facial performance capture. We think so, at least. And you never leave the editor. You do all of these with a handful of assets in the editor, nothing else. So, we're almost done. I think these are some of the most salient points. Now, why rigs in semantic space pay off? Our rig parameters are in that space. That is to say, it is what is activating and where is that activation at in a normalized range, right? So you have like Joe up and down, 0 to 1, or things from 1 to -1. That is opposed to things like geometric or volumetric approaches, where someone might directly describe the position or the rotation or of the joints or of the solver points. The fact that this is in semantic space means that in practice, every animation will always work the same on any rig logic or faceboard-based rig, which of course is all of the meta-humans or anything that you do that you're okay rigging in that space. There's no crumpling faces, no poor lip or eyelid seals or interpenetration or anything like that. Now, your animation might resemble the actor or actress the most when it is on their performer rig, the one that we create in MetaHuman Animator for the solving, but it just doesn't break when you move it on to something else that might be their actual character. Okay, so performance capture requires real-world devices. We'll talk very quickly about that. If you're interested in high-end devices, we support stereo couples. If you want to be more on the compact side of things or on the lower budget side of things, we support iPhone 11 and up. Everything in between, basically, workflow-wise, becomes possible. You can have some actors with stereo couples for your highest quality shots, or you can have actors with iPhones for ready pickups or things like that. You can set up audio booths with performance capture on a tripod. Like what you're seeing there is literally, the picture on the desk is literally what we use to test things. It's a tripod with an iPhone on top. You can have your performers work remotely by just sending them a small device, or they probably already own it, to be perfectly honest. And all you need to get back is some files, or they'll send you the device back. If you're head mounting, it will only provide you with a facial animation, and you're likely to get the neck from your suit. You don't want this to interfere. But if it's on a static mount, like a desk tripod, it will provide a very accurate estimation of the upper neck. Now, last few things, it's important to know this is a device-agnostic solution. We chose to directly support the iPhone because they're convenient, they're widely available, they're very uniform in specs, but we do nothing with it other than capture video and that. We're not using ARKit or anything like that. We support vertical stereo couples because they're some of the most reliable and available configurations, but we're not married to stereo in and of itself. We just do depth inference from it. So this release focuses on fidelity, first and foremost. Part of this is the quality of the results coming from our approach and the way we solve data. We don't do any processing on device, and the result, the quality of the results scales very well with the quality of the data. We don't hallucinate any details. We're not against adding post-processing things later on, but we felt that for the first release, we wanted to do something where you get the animation that represents exactly the performance that was put into it. While we do scale well with the quality of the data, it is not done at the cost of resilience. So, of course, if your actor is covering their face, we're not going to hallucinate their eyes or something that is missing from the frame, but we recover from those things. You don't need to split takes, right? Having good lighting is nice, but this is entirely independent from what is happening in the background. You have bright lights, you have movement, it doesn't matter. It's perfectly resilient to all of that. Now, oh, sorry for that. The quality of animation. When we say quality, we don't mean it in some vague sense. We don't even refer to issues like noise. We're particularly well behaved there too. But what we mean is that the function curves that come out of these systems are very well behaved. Semantic space solvers can sometimes choose to interpret different poses that are temporally adjacent with different controls. And when that happens, you'll see curves crisscrossing. We don't have that problem, just don't. The animation that comes out of these is always very good. It's always highly editable. Okay. So, last feature, audio to tongue, is what it sounds like. We solve basically solely based on video and depth streams, which makes it resilient to things like audio slips or missing audio and so on. Chances are in your shoot, you do have audio, so we should be making good use of it. Part of the solution is audio to tongue animation. It will reliably produce tongue animation from just the audio track in the capture if one is present. And last but not least, our output is a plain animation sequence. MetaHuman Animator for now is closer to content creation than it is to runtime. And we know that you want unencumbered projects and builds. So once you're done solving a performance and you're happy with it, all you have to do is export the animation. It becomes a plain animation sequence and you're done. It's readily available, easy to be moved between projects. There's no need to do anything to it. All right, so that was a lot for half an hour, and I promise I just scratched the surface. We're on the expo area where you can see these live if you're interested. And with that, I'd like to get Matt in, and thank you very much for your time. I hope you have a great GDC.
Hi, how's it going? My name is Matt. I'm part of the advanced character team here at Epic. I'm pretty excited to be here today to show you some of the cool stuff we've been working on. So many areas of Unreal technology have advanced hugely over the years. We have Nonite and Lumen that allow us to represent highly detailed and beautifully lit environments. And with our awesome facial technology you've just seen and MetaHuman Animator, we can recreate the subtleties of human performance and emotion. But we want to bring that same level of deformation quality to our character bodies. So currently, a typical body deformation setup for a real-time character is a combination of additional helper joints and sometimes corrective blend shapes that attempt to preserve the volume and silhouette of the character as it animates. In fact, our metahumans use a helper joint system to do exactly that. But human biomechanics are extremely complex, and this type of setup is always going to be limited in what they are able to represent. So building a system that allows you to see the scapula moving underneath the muscles or the skin sliding over the rib cage as you raise your arm is always going to be a real challenge. So what we want is to bring our characters to life with the awesome muscle and flesh simulation that's available to us in Houdini. Now, these deformations look great, but the simulations are computationally very expensive. So what you see here is taking around a minute per frame to solve. So wouldn't it be great if we could have this level of deformation complexity but able to evaluate in real time? Well, what we are now able to do is to use machine learning to compress that simulation data into a format that can be evaluated at runtime. So you are looking at our ML character with deformations driven by full muscle, flesh, and cloth simulation from Houdini. It's running in real time and on PS5. It's taking around 1/10 of a millisecond on CPU for network inference, and as you see it here, around 1 millisecond on GPU for morph target evaluation. So this is a fully generalized model. We have not just trained it on the cinematic animation that we can see here. So this is our character. His name is Emil. He is an anatomically correct digi-double. He was authored from 3D scan data of head and body, and we also captured full body MRI data, and we used this to help build and validate our musculoskeletal system. This was taken into Houdini, where we work closely with our friends at Side Effects to set up full muscle and flesh simulation. Now, a lot of the Houdini tools we used are under active development. Even so, the results we're getting out of it are pretty awesome, and they're only going to get better in the future. And at this point, I also would like to thank our actor for giving us permission to use his digital likeness and for allowing us to create the simulation data that we use to train our different machine learning techniques. each technique is referred to as a machine learning model. And this is a neural network that maps the value of some inputs to some output data. So for our particular use case, the inputs are joint orientations, and the output is the mesh deformation that matches our training data. For efficiency, we encode this deformation as a series of learned morph target shapes, and our network outputs the weights for these. So we have different types of model available for us to use in Unreal. Each uses a different ML technique, and each has their own strengths and weaknesses. There is not one single model that is appropriate for all applications. So we created 3 deformers in total using 2 of the models available to us. The neural morph model gives us really great results for flesh, but performs poorly for cloth. So for these areas, we used the nearest neighbor model, and this is able to better reconstruct the complex folds and wrinkles that we want to see forming as the character animates. So the total vert count for our character is around 315,000 verts, so it's fairly high res. Joint count is pretty lightweight. We have 91 bones, and this does include the fingers. Each of the models took around 50 minutes to train. So if you have a CUDA-enabled card, we can use GPU acceleration, so this makes training pretty fast. Now, we'll cover these models in more detail, but let's take a step back and try and get a high-level understanding of what they're actually doing. So each deformer begins with 2 versions of the same character asset. We have a very simple one. This is just a basic joint hierarchy and linear skinning, and this also becomes our skeletal mesh asset in Engine. Then we have the complex one. So for us, this was the muscle, flesh, and cloth simulation generated in Houdini, but really there are a ton of different deformations that you might want to learn depending on your technical and creative goals. So the basic goal is to learn the delta, or the difference, between the complex and simple example across a range of poses, and then compress that information into something that can be evaluated in real time. This is the training process. The result of this is an ML network and a series of morph targets packaged into our ML deformer asset. When we apply this to our simple skeletal mesh and animate it, the resulting deformation should closely approximate our complex training example. Now, we need to give the models lots of examples of the character in lots of different poses so it can learn what the deformation should look like across a wide range of animations. This is the training range of motion, or ROM, and it's perhaps the most critical element of the process. Now, it's important to note that these models can only learn static deformations. They are not able to learn dynamic properties. But the muscle, flesh, and cloth simulation in Houdini are dynamic in nature. Muscles are affected by gravity and inertia, and folds and clothing will form differently depending on how you got into that pose. Now, this presents a problem, because it means we're potentially trying to learn conflicting deltas for poses that have shared characteristics. And what will happen is that these will get averaged out, and sometimes the ML result can lack a lot of the clarity and the detail that we want to see coming through from our source data. So how do we work around this? So firstly, in Houdini, simulation parameters that look good for a continuous test animation are not necessarily the optimal setup for generating ML training data. So the goal here isn't necessarily for the simulation to look good in motion, but to minimize the differences in result for poses with shared characteristics. So we want to encourage folds and wrinkles to form in the same way, for example, when the character raises the leg. We want to simulate muscles relaxing and contracting, and we want muscle-to-muscle collision, but we don't want the effects of gravity or inertia to be present in our training data. There is an additional complication here too, and that is that the random poses in our training ROM mean that the pose difference from one frame to the next is pretty substantial. Now, we can't simulate this sequentially because the resulting velocities are too high for the simulation. So to work around this, we implemented a 10-frame warm-up and settle into each pose. So for each pose in our training ROM, we animate into position over 7 frames, and then we let the simulation settle for 3 before saving out the frame. So these additional frames were generated procedurally in Houdini. So let's look in detail at the models. So firstly, the neural morph model, the local neural morph model, tries to generate morph targets while looking at each individual input. And this results in many small localized networks. The global model, on the other hand, generates a single fully connected network. Now, there are some big advantages to choosing local over global, and this should be considered the default approach. First of these is performance. If you look at the network diagrams on the right, each line between neurons represents a computational cost. So you should be able to see that as we add more inputs, outputs, or layers, the cost increases rapidly for the global model, whereas the local model scales much better to increased network dimensions. Global mode, however, can potentially look further than just around the bone. So in some cases, it can be better at learning deformations that are the result of multiple inputs. To improve local model reconstruction in these sorts of cases, we implemented bone associations. And this allows the model to consider multiple inputs in specific user-defined cases. So for the upper body, we created associations between the clavicle and the humerus, and this significantly improved reconstruction in the shoulder area while retaining almost all of the performance characteristics of the local model. The other key advantage of the local mode is that it will converge to a well-generalized model much faster and with less training data than global. So for the upper body flesh, we trained on around 7,000 frames, but I estimate we'd need around 50% more to get a similar result using the global model. The nearest neighbor model specifically targets cloth reconstruction. So cloth in particular, it's a real challenge because it's highly chaotic and very connected in nature. Even with a careful simulation setup, more complex garments, the nearest neighbor model is going to outperform the neuromorph model every time. So this model starts with an initial PCA layer, and it's trained with a large set of random poses. So for the upper costume, this was the same set that we used for the flesh. Then on top of this, we add an additional layer of simulated fix-up poses, and these are taken from our target animation database. So this is the nearest neighbor data set. During animation, a nearest neighbor function evaluates the character pose, and it applies the closest shape from that set to the character. So on the left is the nearest neighbor model with just the PCA layer active, and on the right, you can see how the additional nearest neighbor set improves the fold reconstruction. So to help generate the optimal set of nearest neighbor poses, we've implemented a k-means pose generator. So given a set of target animations, so typically these would be your game or cinematic animations, and a max pose value, it will generate a set of poses that most efficiently cover that animation space. We simulated our clothing for these additional poses in Houdini, and then we trained our additional nearest neighbor set using this data. So before we dive into Unreal and take a look at the workflow, let's get a high-level overview of it. So the first step is to generate the training ROM animation. The aim of this is to provide the training process with lots of examples of what we want the deformation to look like in lots of different poses. So currently, the easiest method of doing this is to use our Maya PoseGen tool, and this will generate a random animation. The second step is to generate the training data using this ROM. So we're going to use this in two places. First, we're going to apply it to our simple linearly skinned character, and we'll export an FBX of this. Secondly, we're going to apply this to our complex offline character. So for us, this was the muscle and cloth simulation in Houdini. We're going to run a simulation for each frame, and we're going to output the result as an alembic. The FBX and alembic are imported into the engine. We set our training parameters, and then we train. And once completed, we're going to test the results using novel animation. So we should always test using different animation to that which we trained on. And this allows us to understand if a model has generalized properly and is going to be able to perform well with any animation applied. If at this point there are particular poses that are not reconstructing well, we can go back to the ROM, we can add poses to give additional coverage, and we can run through the training process again. So getting to a good result is an iterative process. All right, so let's take a look at this in Editor. All right, great. So the first thing I'm going to do is I'm going to create our ML deformer asset. So once we load this up, okay, so the first thing to note, up on the top left, this is where we can choose which model we want to use. To the right of that, we can choose between training and testing mode. So we're going to start out in training mode. On the right is where we add pointers to our assets. And then here is where we can set various parameters for our network and training process. So the first thing I'm going to do is I'm going to add the Scarlet Mesh. I'm going to add our training ROM as an anim sequence format. And then I'm going to add our training ROM that is the imported Alembic. So this came from simulation. So the geometry cache for that is pretty big. It will take just a second to load. All right, here we go. Now, on the left, we can see our training base. So this is our simple linearly skinned asset. And on the right is our target. So this is the thing that we're trying to learn, right? And this is what came from simulation. If I scrub through, we can see a matching training ROM running on each. And during training, what we want to happen is for it to learn the delta or difference between the simple and complex and then compress that information into something that we'll evaluate in real time. And we can see that delta visualized here with these green lines. So once we're happy that we have two matching ROMs, we can start setting our network up. So the first thing to notice here is where it says include bones. This is checked. So we're going to train using bones as inputs to the network. We could train using curves if we wish. So if we're using bones, we can only consider orientations as input and not yet translations. Underneath here, where it says bones 91. So by default, it's added every joint in my skeleton as an input into the network. Now, to get the best quality ML results, we want to reduce the number of inputs to the network as much as possible. So the easiest way to do this is to start by clicking this animated bones only button. And it's going to populate a bone include list based on the animation. So you can see we start off with 91, we're down to 25. That's pretty good, but we can go further. So you'll notice here it has included the roll or twist joints. Now the transformation of these can actually be described in terms of other input to the network. So we don't need to include these as discrete entries. So I'm going to go ahead and remove those. Oops, missed one. Right, and now from our initial starting set of 91, we're down to 15 inputs to the network. And this is the minimum set of inputs we need to describe the deformation that we are trying to learn. All right, so this is a critical step. Underneath here is where we can set up bone groups. We mentioned that earlier. Down here, we can choose between local and global models for the neural morph model. We can set the number of morph targets, the number of training iterations. Here we can play with the network dimensions. So increasing the number of hidden layers gives the network the potential to learn more complex deformations, but it does come with increased CPU inference time. Down here is the morph target compression setting. So we can change these after training. Modifying these values does not require us to retrain the network. And finally, under here, we can apply a mask to paint masks out for the ML deformed deltas if we wish. And this uses vertex color channels on the Scarlet Mesh. So I'm going to just set the max training frames to 50. This will not generate a usable network, but it does allow me to show you all of the elements of the UI as they pop up. Right, so once we're happy with our settings, we're going to go up to the top left and we're going to train the model. Now what's going to happen to start with is we're going to cache a bunch of information for those frames. Once that's completed, it's going to go into the training iteration loop. So on the left, we can see this training iteration number increasing. And on the right, there's this average loss number. So this number represents the error between the current state of the network and the target deformation we're trying to learn. Right? So a smaller number basically means you're getting a better reconstruction result. So what we want is, as the iterations go up, for this number to come down. Now, initially, it'll start dropping really fast, and eventually it'll flatten off altogether. Now, we don't have to wait for all of the iterations to complete. We can actually click cancel. It will extract our morph targets for us. Because I canceled it earlier, it asks me if I want to save the partially trained network, so I'm going to go ahead and click yes. Right. Now, as I said, 50 training frames is not going to generate a great result, so let's take a look at our actual flesh deformer. So once we've trained, we want to go into testing mode. Over on the left is where we add our testing animation sequence, so we just have the cinematic animation applied here. Underneath is where we apply the deformer graph. This is what's driving the skinning, the morph targets, and it's recomputing normals for us. And I can scrub through. and we can see the animation playing on our ML deformed asset here. We can modify the weight and see the contribution that the ML deformer is giving to our character. All right, so the next step, I want to set up a blueprint for this. I have a partially set up skeletal mesh actor blueprint. I've assigned my skeletal mesh to the component. Down here, I've assigned the control rig and our deformer. So adding an ML deformer to this is super easy. All we have to do is add an ML deformer component and then find our ML deformer asset and apply it here. Now, if your blueprint has multiple skeletal mesh components, the way you create an association to a specific one of those is by using this component tag here. We would add an entry and then simply type the variable name of your skeletal mesh component in here. We can also stack multiple deformers on a single skeletal mesh component. But I'm happy with this, so I'm going to click compile. I'm going to close this down. So I have this blueprint dragged into the scene here. If I open up the sequence and enable the control rig, if I very simply, oops, why is that not working? Okay, I'm just going to switch. This is a live demo. Oh, dear. Oh, of course, yeah, it's a live demo. Right, never mind. What I really want to show you was we can manipulate the control rig. I can drag up the clavicle control. We can see the skin sliding over the abs. It's a fully generalized network. You can animate that. You can keyframe it in Unreal, and it looks great. I'm sorry, I can show it to you. So the most important part of this is the training ROM. So the models are good at interpolation, but they're really bad at extrapolation. So to take a simple example, if my game animation rotates an elbow from 0 to 140 degrees, we don't need an example for every degree of rotation in the training data, but it does need to encapsulate that full range. So if the model is reconstructing poorly, the two most likely causes are either you haven't used enough training data and the model hasn't generalized, or the animation is pushing the character outside of the pose space we trained on, and the network doesn't know how to handle that. So when this happens, the deformer doesn't just handle it gracefully, it won't just stop adding deltas, you're actually going to get some pretty nasty deformations. So it can be really easy to get caught out by making incorrect assumptions when you're setting up the training ROM. So you might have assumed, for example, a planar rotation for the elbows, but forgot that animators like to break stuff, and the performance capture data is often going to have small rotation values on all three axes. So if your training data hasn't accounted for these rotations, you're going to start hitting problems. So one of the issues we had was caused by excessive twist on the clavicles in our cinematic animation. So the training ROM assumed a total range of around 20 degrees, whereas the animation was pushing way past that to 70 degrees. So we can see this in our animation curves here, right? So on the left is our random data that we use for training, and on the right is the cinematic performance. And so you can see that the upper and lower bounds of the cinematic data extend outside of the training range, and we get the mesh collapsing in as a result. Now, in our case, we actually modified the animation rather than the training ROM, and this fixed our issue immediately. So for single animations, like in our case, it's actually pretty easy to debug this kind of stuff because we can just bring the training ROM and the cinematic into Maya, and we can look at the anim curves, right? But we do need better tools in place to debug these kinds of issues against large animation databases. So currently, generating a random training ROM, like you see here, using our Maya PoseGen tool is the easiest way of creating training data that we can be confident covers the full pose space of our character. So for each joint involved in the deformation, we're defining a min and max order rotation value for each rotation axis, and then the PoseGen tool generates a random animation based on those values. But this is kind of a blunt tool, right? It has no understanding of biomechanics, and we end up generating a ton of poses that are not physically plausible, and they're just not useful to train against. So here are some examples of this. So the tool has generated counter rotations along the spine. The biomechanical relationship between the clavicle and the humerus is not being respected. So generating training data can be a real challenge. So we want to make our training ROM as efficient as possible by reducing the number of bad poses. So in Maya, we set up a simple set-driven key system to drive the spine joints, and then we generated the random data using those attributes instead. So this ensured that the poses on the spine remain in a physically plausible space. We also ran a post-processing script to nudge the clavicle rotation values based on the orientation of the humerus. So by making the training ROM more efficient, contains less bad poses, we're able to use smaller training ROMs. So we are often asked about the structure of the training ROM. So does it have to be random? Can we use a continuous range of motion, maybe from a motion capture session? So the table above shows the dependencies between the model we can use and the type of training ROM. So for ML, we actually adopted a bit of a hybrid approach to this. So we use just under 7,000 frames of random poses. This goes the generalized model that allows it to perform well with a range of animations applied. We can even manipulate individual limbs using control rig, which I wish I had have shown you, and the deformations work really nicely, and the model is stable. We then refine that model with a small set of additional poses taken from various motion capture sessions. So currently, this is the approach I would tend to recommend, and that's to build a solid generalized model using your random data set, and then you can refine the result if you need by adding key hero poses from your gameplay or cinematic animation. Now, ultimately, we do want to reduce the need for using random data, and we want to move towards using smaller, more efficient structured ROMs of continuous motion. So we feel that this will offer a more intuitive approach for people to generate their simulation data, training data, rather. And it will also bring secondary workflow benefits when using simulation data as source. The local neural morph model offers some support for this already, and we do expect to ship an example structured training ROM with 5.2 release. So there are a few points to consider in the pursuit of getting better results. We've covered most of these already, really, but one important point is that your simple scalable mesh asset should still include twist or roll joints. So for those not familiar with rigging, these are additional helper joints that distribute twist in regions such as the upper and lower arms and legs, and it kind of removes that collapsing candy wrapper effect that we can see here, right? So without these, the delta that the ML deformer would need to apply to correct that pose is pretty big, right? So ML deformer is, in effect, a lossy compression. So with really large deltas like this, that error can become noticeable, and you might not get a great result. But by including the twist joints, the size of the delta we're trying to reconstruct is much smaller. Any error present is not going to be noticeable. So just to briefly cover performance, the table on the left gives a PS5 performance breakdown for each of the 3 deformers we used. To recap, we used the neural morph model in local mode for flesh and the nearest neighbor mode for clothing. The flesh layer running on the neural morph is super performant, actually, it's great. The nearest neighbor model has a slightly higher cost, and this is due to the additional nearest neighbor data set that increases memory usage and GPU time. On the right is a table of the network parameters that have the greatest effect on performance. So 0 delta threshold culls small deltas from the morph target set. This reduces memory and GPU time, but in some cases can introduce artifacts. Compression level is fairly self-explanatory. Higher numbers affects memory usage, but could introduce artifacts. Increasing the number of morph targets gives the potential for better reconstruction results, but with a higher memory and GPU cost. And as we mentioned earlier, increasing the network dimensions gives the potential to learn more complex deformations, but at the cost of increased CPU inference time. Now, for the nearest neighbor model, PCA coefficient number and nearest neighbor data can be seen as broadly analogous to the number of morph targets, and this affects memory and GPU time. So to sort of wrap up, given the right training data, the reconstruction and performance characteristics of the current models are actually pretty good. So the main challenges right now are around workflow and generating the training data. This has a big impact on accessibility and scalability. So what we have shown here today is achievable for a hero character, but we need to make workflow improvements to extend this out to secondary characters. We need alternatives to random ROMs. We need models that are less sensitive to being slightly outside of the trained space. We need support for multiple pairs of anim and geometry caches, and we need better debugging and visualization tools to help find the solutions to problems when things aren't working. We will be releasing this as a sample project with 5.2 later in the year. We will also be including all the geometry caches and all the source data. That includes the full musculoskeletal model that you guys can learn from, take apart, and hopefully repurpose for your own ML Deformer projects. We would love for you to come and chat to us at a booth. You can get hands-on with this demo. You can change cameras, switch between musculoskeletal, flesh, and clothing layers. You can pause the action, and you can see the deformation result both with and without ML Deformer running. And finally, I just want to thank everybody that worked on the project. I want to thank Side Effects for their help and support. You guys are rock stars. And thank you to you guys for your attention. Thank you.